is Juan Shi from the program of Brain and Cognitive Engineering department. And today I'm going to talk about the two important topics in machine learning, the algorithm fairness and the graph neural network. So first, let's start with the fairness. This paper is published in ICM 2019, and there are two important aspects in this paper. The first one is this paper provides a new metric of fairness, which is called as an EE531 fairness, and they also did the proof of concept in the data-driven way. The second important thing is that they implemented a micro-scale model of decision making, and they showed that how whole population changes through the individual level behavioral change. So in this study, they used a student performance data set with a classical supervised learning setting. So here there are several features, and there are corresponding grades of students. So here, the I denotes the individual, and the X denotes their features, and the Y denotes the ground truth label of their grade. So they assume that there existed function h from x to y, and this actually predicts the y from the given feature. So this predictive model is estimated from three different models: the neural network, linear regressor, and the decision tree. And actually, this predictive model is used for predicting the grade from the feature. So this H also used for predicting the change in grade when the student has changed their feature itself. Like when students did more effort to do something, then the predictive model H can predict the change in grade from their changed feature. So, and they also assume that there are the benefit function which quantifies the benefit when they have the certain features. So here the benefit function is defined by the parameters with the ground truth label and the predicted label. However, in this paper, for the simplicity, they they set this benefit function as a predicted grade. So, and here the grade are or scaleized or normalized to have the some better feature when their grade is high. So this is the notations. And in this study, there are three major components are suggested. So first one is the reward function. This reward function says that the added benefit when the individual I changes their features. So here you can see that this is the changed feature, and this is the original feature, and this reward function is defined by the difference of them. And here in this study, they set this alpha as 1, and as I told you, this is defined as the predicted label from the model, three different models. And second, the utility is defined by the difference in the reward and the effort. So reward is what I mentioned already, and here the effort means that the sum of the effort to change each features from x to x prime. So there are some constants for the group S, which means that the effort constant is different across the groups. And here you can see that there is a specific constant, and there are also some constants for each features, which is multiplied by the feature level effort and the sum of them. So this is the effort function.
What was the neural alpha?
Alpha? This is just kind of term that scalarizing those benefit function. So it can be any flow between 0 and 1.
Between 0 and
Yeah. But in this study, for simplicity, it is not necessary to be 0 to 1. So it is just making some scale to the benefit. positive?
Should be positive.
Yeah, it should be positive. Okay. So here is the notations used in this paper. Okay. When you look into the previous and related works on here, so the fairness concept has been really much focused on recently in ML field because it has not been deeply considered so far. So the existing notations are mostly one-shot and assumes the equal error across different social groups. So here a bunch of studies came out, and there are so many metrics which focused on the different real problems, such as like disparity impact, or the equality of oaths, and so on. And on the other hand, there are some studies which shows the real impact of decision-making model or the individual behavior in the policy algorithm. So you can see that there's a delayed impact model, which means that the policy change could introduce the long-term change of the whole population. And the other paper also says that the individual level affirmative action can affect the whole population.
I have a question. What's the meaning of one-shot?
One-shot means that, well, I'm going to talk about it in this slide. So one-shot means that they usually do not consider the dynamic property of behavior and features. So given the data, they only like do the snapshot of their features and the labels, and they try to figure out their segregation indexes or something. But in this study, they try to reflect the dynamic property of behavior and features, which means that in the real world, actually, the individual level features are supposed to be changing, which means that it's dynamic behavior something.
So the feature of individuals can change?
Yeah.
Can change?
And the author says that this effect says as an effort, which means that so far the models cannot capture the disparity in the effort, which means that even they do the same, they have the same effort, but the different social groups might have the different effect from the same effort. Okay? And the second part means that so far in the decision-making model, actually the individual level effort is not considered, which means that if there is a whole population, and for each individual, they might do some effort to change their feature themselves. However, this phenomenon is not considered so far. So in this study, they provide a group-dependent and data-driven measure of effort fairness. So they set the effort fairness and they did a proof of concept. So here they emphasize the dynamic property of unfairness. So in the microscale model part, they simulated the dynamic change in society through the individual level effort. So it means that they try to figure out how the individual level behavioral dynamics and the human responses shape the long-term impact in the whole population. So the other novelty of this paper is actually they mimicked the actual social phenomena. So this study is inspired from the equality of opportunity, which means that the effort is proportional to the social group. And the second paper they inspire from is the social learning, which means that in the social learning model, actually this is from the societies. In this model, individuals try to follow the role model. So it means that individuals imagine their role model from their cell population, and then they try to change their features if the features are immutable. So,
I have a question. But is it proportional to rank the first, next, and expire?
Yeah.
Is the visual of the paper or the assumption?
Actually, it's not an assumption, but actually this result is from
so the visual
this study. Yeah, right.
Study.
So if there are some separate social groups, then within the social group there might be some distribution of some features, specific features, and if individual have the feature X, so you can plot them in the distribution itself, and then they try to change or not according to their X within each social groups distribution of feature. Okay. Yeah. So let's take a deeper look into the algorithm. So here the basic idea of this new fairness metric, the effort-based fairness, is that even two groups have the same, I'm going to say it's an error, but the effort to fix them is different. So they provide three different concepts. The first one is bounded effort unfairness. So this metric says that there is a upper bound on the level of effort for a specific group. So if you can see, if there is an individual I here, given the bounded effort delta, to change their feature from Zi to Z, which is a role model. So if there is a bounded effort, then there would be some maximum reward that individual can get. So the expectation of this individual's maximum reward from the bounded effort is defined by this bounded effort unfairness. So from the data set, which is the student grade data set, you can see that there are different gender groups shows different reward when the effort bound is same. So you can see that if the effort is fixed as 0.2, then each group has the different number of average reward.
How to obtain this figure?
This figure uses this data set. So here. So from this data set, they firstly do the classic supervised learning to get the predictive model H. Okay, and then
so the figure is obtained from the real data.
Yeah, right. The real data. So I'm gonna say this is a proof of concept. So they just suggest.
So the second question is the bounded effort of fairness.
Yeah.
Is defined on the as I is equal to S.
Right. So these features are, how to say that? So it means that there are some sensitive features. So here that is the gender, male or female. So for the individuals who have the sensitive feature S are
so the unfairness.
Yeah.
So in this definition, the unfairness means the different values of the
average
formula.
So these unfairness are seen to be different across different groups. Okay. I think this figure have much more things to say because there are some like reversing effect across the different bounds, but they didn't mention about that.
Sorry.
And the next, the second one is the threshold reward unfairness. So here, this metric says that there is the minimum effort to get a certain amount of reward is different across groups. So here, it's actually similar. For individual I, if you'd like to get certain amount of reward or of delta, then there are some minimum effort that you have to do. And it says that this value is different across groups. Yeah. So here also, gender groups shows the different average effort when they try to get the same amount of reward. Okay. So this is the second metric. And the third one is effort reward unfairness. So here, this effort reward unfairness says that how much utility can this group get? So it says that the representative sample in the subpopulation, which means the maximum utility. So from the specific subpopulation, there are some max utilization within the group. So here the others compare this metric with the existing fairness notions, the positive residual and the negative residual. So, and the author says that the previous fairness matrix does not capture perfectly this disparity in the manners of this effort-weird unfairness. Yeah.
There are many skips. What's the UH? What's the definition of UH? In the previous slide?
Yeah, in the previous slide, the UH is defined by the reward minus effort. So it means that when the utility is high, it means that you got a maximum reward and you got a minimum effort.
Right, I see. And the figure,
Yeah.
compare 1, 2, 3, 4, 5.
Yeah.
Positive residual and negative residual,
Yeah.
and the effort reward. The effort and reward, the concept of effort and reward, maybe I introduced in this paper, but the previous work does not consider the concept of effort and reward. So what's the meaning of positive residual and negative residual?
I actually didn't get perfectly on that concept. Yeah, but as to my best knowledge, I know that if you divide the population into the subpopulations, there would be some the difference for the specific features. Two groups might have some different features, different distributions in the specific features. So, so here you can see that.
So anyway, the positive residual and negative residual can be obtained by some algorithms, and the algorithms consider utility. Does not consider effort.
That's not considered as a utility. Actually, the measure is done by the disparity, which means that the difference between two groups in the manners of their grade. Yeah.
This is also with the Y.
Yeah.
In the figure, the meanings of Y are different for colors.
Yeah.
The scales are not the same, right?
Yeah, right. But I also wonder that I think this figure cannot capture perfectly that the previous matrix does not capture this kind of unfairness. But in this paper, they provide some like.
In my opinion, this figure is not good.
Yeah,
because,
right.
Because they are too they are.
I don't think so too.
This figure result in confusion because MSE, MAE.
So here I also really confused about that. But in this paper, when they try to claim this sentence, they provide some real examples from the training data that like some of the feature like how they say.
I mean, what's the meaning of Y?
As I know, this is the
disparity. What's the definition of disparity in this figure?
They
maybe
not clearly say that, but to my knowledge, it is difference across different groups, two groups, male and female, in the terms of their grade.
I see. So this figure can be useful because I think at first the scale of Y can be different in terms of the color, but I realized that the scale of Y is the same for all terms. All terms. And the disparity, maybe disparity is defined in a manner common to all terms. So the definition of disparity is important in this figure. Maybe all algorithms consider their own object functions.
Yeah,
But the comparating is done on the common measure, denoted by disparity. And what's the definition of disparity? Should be valid, or it is better to write down the definition of disparity in this case, because there are two diverse methods.
Yeah, right. I surely also considered about that, but I couldn't find any clear sentence about the definition of disparity in this figure in the paper.
But maybe it is the common measure of our method, so the definition of disparity can be found.
Okay. So far, I gave the effort-based measures of the fairness metrics. So let's we get into the micro model of social learning. So here, the basic idea is that the individuals in the group do the social learning, which means that they follow their role model. So each individual in the cell population try to recreate their role model inside their mind, and then they try to change their feature by themselves. So here, in this micro model, individuals try to change their feature to Z prime, which is maximized within the cell population. So here, the authors compare the initial group and the impacted group. So which means that the initial group is just measure their some kind of measures before this social learning, and the impacted group are measured after they do this social learning in the individual level. In the other word, the micro model. So they also use the student performance data set, and the three models are used samely. So here they use the three segregation indices from the sociology study. So first one is clustering, the second one is evenness, the third one is centralization. And all of these indices are good, are better when the metrics are high. Okay, so this is the result of this microscale model of social learning. So you can see that in these graphs, the impacted population shows the improved segregation metrics than the initial population for nearly almost all of the metrics, segregation metrics. So it means that the segregation changes as the result of behavior dynamics model, which means the individual level change might induce the whole population change in the long-term manner. And next, they try to impose the fairness constraints into the model. So you can expect that when they do the intervention to the fairness model, then you might expect that this kind of fairness intervention would reduce the level of segregation. But according to the experiment result, it is not always the case. It is not always true. So sometimes some of the intervention shows the significant decreasing of metrics, which is not good. However, sometimes the larger tau reverse the effect of such positive change. And here, in the sum of the metrics, there were not that much difference across the initial population.
Sorry, in this slide, what's the meaning of tau?
The meaning of tau is actually the paper is not that much kind. So to my best knowledge, I found that during the training, like when they try to get the predictive model, they deploy the constraint when they in the objective function. Yeah. So when they get the H, they deploy the constraint, for fairness constraint here, which is tau. Yeah. So and then get the model.
So I know to question the initial population and infected population.
Yeah.
In the previous slide.
Yeah. Impacted population is the population which did the social learning, the individual learning.
So the infected population is generated
Yeah.
from the original data?
Yeah, from the right. From the original data, this microscale model, individuals follow the role model. So after the one generation, this becomes an impacted population. After the social learning.
Will you explain the algorithm?
Oh, okay. So if there's an initial population, which has x prime, x comma y, and then from this data, this is actually from the real data, and we get the predictive model H, right? And in the micro model, this individual try to see the subpopulations, and they find that the Z prime, which is their role model. So they try to change their feature from Z to Z prime, which means that this predictive H, model H might get actually this is X prime. And this is the new label from the changed feature. Okay, individual level change of feature might change their grade according to the predictive model.
Changing label?
Yeah, changing label. So from the real data, we get a predictive model, and in the social learning model, individual change their features.
Changing the feature.
Yeah, changing the feature.
Yeah.
And then the label is changed at the impacted population.
How to know?
Sorry? How to know?
Label is the ground truth.
Yeah. Well, actually, the training is finished in the step before. So H is fixed. So this H is considered as the input. Input is a input. From the input, there are some grade. This is the model. So here, after the social learning, the individual just change their feature to X from X prime. So this predictive model is used for how this individual's grade is changed. So it means that X prime, which means the new label.
New label Y prime?
Yeah, new label Y prime. And then they measure this type of new segregation index across different groups. So I'm going to say that the new label is generated after the social learning.
I have another question.
Yeah.
In the previous, you introduced many terminologies like effort and bound.
So here,
how these are used to algorithm?
Okay. So I introduced 3 different unfairness metrics, right? However, in this paper, they only use this effort-based unfairness. So here, in the subpopulation, the maximum utilization becomes the representative sample of the subpopulation, right? Yeah. And then here you can see that they use this metric.
In the previous slide, sorry, in this. So the algorithm predict the functions in this formula.
Yeah, right. So So in this formula they use this function H, right?
H
and actually
effort. What is the effort? Effort is the.
Effort
is the function.
Yeah, effort is also the function.
CS is the interceptor and epsilon SK. What's the epsilon SK?
It means that for the specific subpopulation S, for the specific feature K,
XK and SK prime is the argument of epsilon SK.
Yeah.
Epsilon is a function.
Yeah, right. So epsilon SK means that when you try to change feature K in the subpopulation S, and you like to change feature SK to the.
So it's a function.
Yeah, function.
It's a function. Epsilon is a function.
Epsilon is a function.
non-linear function or linear function or any function can be done?
Yeah, any function can be done, but in this paper, for the simplicity, they just linearly subtracted them in this paper. So it can be any type of function, but in this paper, for the simplicity, as I know, those epsilon is just defined by xk prime minus xk, because all the features are normalized.
Alpha, what's the value of alpha in the
Alpha here? Alpha is 1.
1?
Yeah. In this paper, is 1.
Constant 1.
Yeah. So,
Okay.
yeah. They give up some many parameters for the simplicity. So, finally, the summary. So this paper provided two important aspects of fairness. One is they provided the E4 based on fairness, and they provide the microscale model of decision making. So here, the major advantage of this E4 based fairness is that it can capture the fairness in the behavioral dynamics, and there is no case specific assumptions, and this concept is also proved in the real data. So, and here, however, it actually varies across the different predictive model chosen, and also, this paper does not consider the macro level policy here. And also, this paper actually gives up some many behavioral nuances, like some other parameters, or it too much simplified all the behavioral dynamics of people. But however, this paper can be a really great example to show us the importance of considering such effort or the individual effect with the machine learning. So I'm gonna wrap up with the fairness paper here. So can I just continue?
Interesting.
Okay, the second paper is about the graph neural network. And in this paper, the authors tried to solve the few-shot learning task with the graph convolution network. So here the task is basically an image classification task. However, they did the few-shot learning task. So few-shot learning task is a bit different from the classical supervised learning. So here, each class appears only a few times, and then and the agent should recognize a single image without label. And in this paper, the other types of tasks are also considered, like semi-supervised learning and active learning. So here, the semi-supervised learning task is given bunch of unlabeled data that the agent can utilize the unlabeled data. For example, they try to figure out the structure of the data. So that's why it calls it a semi-supervised learning. In the active learning task, the model can actively request a label for the model improvement. So it means that there are some unlabeled samples, and the agent try to ask some labels which is unlabeled to improve their model in the training step. So in the more mathematical terms, the test conditions can be expressed like this. So given the data set T, there are S labeled data and R unlabeled data and T test data. And here, the few-shot learning means that there are no unlabeled data, and there are only one testing data, and the number of labeled data is given as a Q multiplied by K. So it means that the label appears Q. The label appears Q. There are K samples, and there are Q samples are appeared for each group. So each Q shot K way learning. In the semi-supervised learning paradigm, there are more than one unlabeled data, and there are only also the one testing data. And these unlabeled data become the auxiliary images for the training. And in the active learning concept, there are also the unlabeled data here, However, the learner can request the labels from the sub-collection XR. So if the model thinks that that it is necessary to have some more labels, then they just request the label from the unlabeled data. So the one-shot learning concept is firstly suggested in the Fei et al. And actually it uses the Bayesian model for the one-shot learning. And there comes out the other networks such as the CMS network, prototypical network, and matching networks. So in the CMS network, they said that they embedded the image in terms of their Euclidean metric become label similarity. And in the prototypical network, they aggregated the information for each cluster. It means that each cluster in the mathematical term becomes the same or similar labels. And in the matching networks, they deploy the attention mechanism for edge feature learning. And the point is that they segregated the label network and the image network, which means that label network, so label and image has a different architecture within their model. And in the other side, the graph neural network has focused on to utilize the neural network in the knowledge structure like tasks. So in 2016, Keith suggested the graph convolution network to solve the semi-supervised classification task. However, so far, the one-shot learning usually casted as a supervised classification through additional supporting components, which requires really a lot of parameters. So and then the one-shot learning can be considered as a supervised interpolation. However, most of the studies did not utilize so much their graph, their structure-like data set property. So it means that the data set have the property of segregated features. However, they did not explicitly use those features in their model. And we also need some more generalizable training concept, which means that the model which fits to any types of learning training setting. So here they did the few shots that we supervised the active learning. So in this study, the authors casted the few-shot learning problem to the message passing task. So they utilized the graph neural network model to construct an end-to-end model for the few-shot learning image classification task. So here they used the graph convolution and they achieved the state-of-the-art in the few-shot learning with so far less parameters. And they also extended the few-shot learning model into the semi-supervised and the active learning model. Now let's get into their implementations. So in this study, they set each node as a single image and made the graph propagate the label information from the labeled nodes to the unlabeled nodes. And here the edges are trainable, which means that the edge is the relationship across the data. So it is also become the message passing task because from the labeled data set, they train the edges and the whole model can propagate their information to the unlabeled images, nodes. And here they use the posterior inference over the graphical model for the final classification. So the main architecture can be divided into the three components. The first one is the latent calculation part. So here they try to classify the image or handwritings. So they use the convolutional neural network for getting the latent. And then after the latent are flattened, then they use the multi-layer perceptron for constructing the metrics, graph metrics, and the adjacency metrics. And the final step of this graph convolution block, graph network block, is the graph convolution part. So one GNN block can be described as this figure, which contains this matrix construction, and the graph convolution. So more precisely, they used two different data sets. One is OmniGlot, and the other one is Mini ImageNet. Sorry for the typo. And actually, the architecture used is a little bit different, even the major points are same. So here, from the OmniGlot, it is kind of really simple image set. So they use a relatively simple latent layer as a CNN. And then they did a 64-dimensional embedding, and then they used three layers of graph neural network block. In the ImageNet, mini ImageNet task, it is also same. So there are four CNN layers, and then the latents are embedded into the 128 dimension, and then they use the three graph convolution block. But in this case, the task is relatively complicated than the OmniGlot, so they use the dropout in the CNN part. So as I mentioned, they use the two data sets. One is OmniGlot, and the other is Mini ImageNet. And for the OmniGlot, they use the 1200 data as a training data, and the 423 data for the testing. And here the Mini ImageNet, they have a 64 training classes and the 20 test classes. And actually, all of the few shot and the semi-supervised learning are done in the Q-shot K-way. And the training is use the cross entropy at each node. And in the active learning setting, the image querying is done after the first GNN layer. So they apply some function, they train some function, and then use for, and they put the unlabeled data into the function, and then they get some attention vector. And from this attention vector, they request the label from the data set, and then they do the label concatenation. So these are done just after the first GNN layer. And as same as the testing, same as the training, testing also uses the K-shot and Q-way, Q-shot and K-way. So it means that they sampled K random classes and sampled Q random samples. And here the accuracy is just defined by the percent of the matching ground truth and the predicted limits. So here is the experimental result for the few-shot learning test. So here you can see that they achieved the state-of-the-art compared to the other pre-existing networks. And one interesting thing is they really efficiently decrease the number of parameters using the graph neural network. So you can see that for the OmniGlot, for the ImageNet, they all use much less number of parameters if they get a similar or more better result on the real data set. And in the semi-supervised learning task, you can see that the accuracy is similar or better than the normal supervised learning cases. So it means that the semi-supervised learning is helpful for learning the relationship between data in here. So it means that graph neural network might this might be because the graph neural network try to get the relationship across different data. So that's why this semi-supervised learning works. Finally, in the active learning task, you can see that it shows the enhanced performance compared to the random sampling case. So it means the random label requesting case. So this random means that they request the random labels in the unlabeled data. In the active learning, it requests using some additional module in it means that the active learning is also applicable for the GNN future learning agents. And actually, the small amount of change is due to the performance saturation. So here's the summary of GNNs. The suggested model casts the future learning to the message passing problem. So it means that they use the GNN for the future learning. So they could make the end-to-end GNN model for the future learning. And also they could extend the future learning to the semi-supervised and the active learning to the graph neural network. So here is the overall summary of today's presentation. So for the fairness, we've seen the E4 based on fairness, and we also see the micro model reshapes the whole population. And in the graph neural network, we saw that the future learning task can be casted to the supervised message passing test, which can utilize the GNN to construct the end-to-end model. So in this paper, they achieved the sort of with using less number of parameters, and they also could extend the model to the various training results. Here is the references, and thank you for listening my presentation.
그 알고리즘 그림에서요. 각각의 노드가 인지한다는 점을 얘기한다고 했잖아요.
네.
이거에 대한 스케일에 대한 이야기는 없었나요?
스케일러빌리티라는 게, 근데 이게 사실 레이턴트가 계산된 걸로 여기 만들어진 거니까.
그러니까 원래 뭐 풀사이즈 이미지나 뭐 이런 거 100만 장이 있는 거잖아요. 뭐 오픈 이미지 같은 경우에 800만 장이 있고 노드가 800만 개를 다룰 수 있는
근데 이거 근데 제가 이해하기로는 이제 큐샷 K웨이에서 그만큼의 데이터라, 아까 항상 QK만큼 샘플링을 한 다음에 트레이닝을 했다고 하더라고요.
샘플링을 한 다음에
네. QK 그만큼의 샘플이랑 테스팅이죠. 그걸 해서 이제 했던 것 같아요. 개수가 얼마 안 되니까
그리고 실험한 데이터셋 사이즈가 그렇게 큰 건 아니에요.
네.
그 다음에 이 전 슬라이드에서 여기서요 매트릭스 컨스트럭션이 3개씩 들어간다는 데
사실 저도 그러니까 사실 그래프 컨버전 하고 나면 내나 그래프니까 다시 이걸 할 필요가 없는 것 같은데 그 블락이 3번씩 쓰였다고 일단 뭐 말은.
그래서 매트릭스 컨스트럭션이 어제이선시 매트릭스라는 거잖아요.
네.
그거를 3번을 만든 건가 아니면 이게 정확히 저렇게 언급이 돼 있었나요?
그러니까 이렇게 블락을 설명해 놓고 이 블락을 3개 이용했다 라고 돼 있는 그게 너무 앰비기어스하게 써져 있더라고요. 근데 그러진 않았을 것 같아요. 저도.
매트릭스 컨스트럭션 어제이선시를 한 번 만든 다음에 그래프 컨버전을 3번 통과시킨 거는
저 그거는 말이 되는 것 같은데 뭐 레이어 다음에 다시 인베딩해서 다시 했을 리는 없을 것 같고요.
한번 확인해 주시면 혹시 실험이나 이런 코드를 보시고 있나요?
코드는 제가 아직 못 봤습니다. 있는 거는 확인을 했는데 코드는 아직 못 봤어요.
아마 보면 그 파이널 레포트에는 저 코드나 뭐 그런 거 확인해서 저기 좀 확실하게 전달이 되면 좋을 것 같고요. 혹시 다른 질문이요? 그냥 퀘스천은 없나 보네요. 네, 수고하셨습니다.
감사합니다.
네. 저희가 채점에 대해서 좀 빠르게
눈이 들어가지고 그 발표를